Hello, everybody. All right, today we are going to take a look at the binomial distribution. And a binomial distribution or a binomial experiment is when you have an experiment where every event has only two possible outcomes. For example, when you flip a coin, that's the best example of a binomial outcome. There are only two possible outcomes when you flip a coin. It's either going to be heads or tails. You can also think of checking the number of male and female babies that are born from, on a given day. There's two options there for each baby that's born. They're born either male or female, and some other things you can consider. You can consider just about anything a binomial experiment if you think of it as this thing happens or it doesn't happen, and shooting goals in a soccer game. So if you are shooting penalty kicks, a given athlete might have, let's say, a 78% chance of making their shot based on previous experience. And so there's a 78% chance that they make the shot. That means there would be a 22% chance that they don't make the shot. So it's either something happens or it doesn't. And so anything that we can categorize into two different possible outcomes, either a success or a failure, can be considered a binomial experiment. So the requirements are here. There must be a fixed number of trials. So we're going to say that we're going to shoot 20 penalty kicks in a soccer game. So there's a fixed number of 20. Each trial can only have two outcomes, so they either make the shot or they don't. These outcomes can be considered as either success or failure. And then 3, the outcome of each trial must be independent of one another. So what happens on one shot doesn't impact what happens on the next shot. So every single shot that soccer player has the same likelihood of making the shot. And then 4, the probability of a success must remain the same for each trial. So that's kind of related to what we were just talking about with 3. If that soccer player has a 78% chance of making the first shot, they also have a 78% chance of making the second shot, and so on. Okay, so let's take a look at example 1. Here we're just going to decide if these can be considered a binomial experiment or not. So if we select 20 college athletes and record their height and weight, this is not a binomial experiment because their height can be many different numbers. It's almost unlimited number of possibilities. It's not a yes or a no. And then the same thing with weight. You could have, if you weighed 30 people, you might have 30 different weights. And so there's not just two possible outcomes. Recording the gender of the first 20 babies born at a hospital in 2021. Yes, there are two possible outcomes. The gender of a baby when they're born is either male or female. And for part C, drawing 5 cards from a deck without replacement. It doesn't really matter if it's with replacement or without replacement, and recording the color of each. So if you're familiar with standard deck of cards, there are only 2 colors. Cards are either black or white, and so that is black or red. There's the black suits, which are spades and clubs, and then there are the red suits, which are diamonds and hearts. So there's only 2 possibilities. Every card is either going to be black or red. So that's, yes, that can be a binomial experiment. And then the last one, selecting 5 students from a large school and asking if they are on the dean's list. That can be considered a binomial experiment as well, because their answer is either going to be yes or no. So there's only 2 possible ways that they can respond. So when we're calculating the probability of a binomial experiment, we have, this is, you might recognize this notation. Remember, that was n choose r, In this case, it's n choose k, so it's the number of combinations. So you can say n choose k, or you can say n items, how many combinations of k. So that's NCR. And remember, we learned to calculate that on our calculator. I'll refresh your memory on that if you've forgotten. And then P is the probability of success. And Q is the probability of failure. And notice that these two items together, these two exponents together, always add up to n, which is n is the number of trials. So there are n trials, and we want to know the probability of k successes. Okay, and so another way to write this, remember the formula for combinations is n factorial over k factorial n minus k factorial. So that's the same, this is the same formula, just written a different way. And again, the n is the number of trials, p is the probability of success, and q is the probability of failure. Okay, so if we toss a coin 5 times, n would be 5. The probability of getting exactly 3 heads would be k equals 3. The probability of success, every time you toss a coin, the probability of getting heads is 1/2. So lowercase p would be 1/2, and lowercase q, the probability of not getting heads, is also 1/2. And so the probability of getting exactly 3 heads is 5 choose 3. And then we take the probability of success and how many successes we're hoping to get, and we're hoping to get 3 successes. And then the probability of failure, if we get 3 successes, then we're going to have 2 failures because there are 5 tosses altogether. And so the reason why this works, 5 choose 3, is because think about how many different ways we can arrange these. So if we have heads, tails, heads, tails, tails, so that would be exactly 2 heads. But how many ways are there to arrange those? So you could also have heads, tails, tails, heads, tails. That's another way of getting exactly 2 heads. How about tails, heads, heads, tails, tails? There are a lot of different ways to arrange these, and the number of ways of arranging the H's and the T's is 5 choose 3. Or sorry, I wanted to do 3 heads, so we can change. We can say there's 3 heads, 3 heads, 3 heads. Okay, so these are just a few of the ways of arranging these so that we get 3 heads and 2 tails. So 5 choose 3, what we're doing, the reason why 5 choose 3 is going to give us the same number of outcomes is because out of the 5 spaces, we're choosing which 3, that one, and that one, for example, where we're going to put the heads. And then, so 5 out of 5 spaces, we're choosing which 3 are going to be heads, and then the remaining ones will be tails. So 5 choose 3, to refresh your memory on how to calculate that on your calculator, you can go 5, math, probability, and NCR is there. So 5 choose 3 turns out to be 10. So I listed 3 of the ways of having 3 heads, but there would be 10. If I wanted to list all of them, there would be 10 altogether. So 5 choose 3 gives me the total number of ways of arranging these, and that can also be calculated as 5 factorial over 3 factorial, 2 factorial, and that'll give you 10 as well. So anyway, if we multiply all this out, we can put it all on one line. So we can do parentheses 5 math probability 3. So there's 5 choose 3 times 1/2 is the same as 0.5 raised to the 3rd power. So I used the caret symbol here to raise to the 3rd power, and then times 0.5 raised to the 2nd power. And so that turned out to be 0.3125, which is 31.25%. So the probability of getting exactly 3 heads when you toss a coin 5 times is about 31.25%. Okay, next example. In this one, the probability of having, if you're buying a package of light bulbs, 1 out of every 100 light bulbs packaged is defective. And so if you have 6 light bulbs, you choose 6 random light bulbs, or you buy a package that has 6 light bulbs in it, what is the probability that exactly 2 of them are defective? So in this case, our number of trials is going to be 6. That's how many light bulbs we're choosing. K is the number of defective ones. So that's kind of, I mentioned this before, it's kind of interesting that defective in this case, we're considering a success. What's the probability that we'll get exactly 2 of them? We're calling that a success because we're trying to measure how often that's going to happen. But obviously, having a defective light bulb is not very successful. But that's just the word success doesn't always mean something good. It just means the likelihood that that thing is going to happen. So K would be 2. And then the probability of defective is 1 out of 100. And the probability of not defective is 99 out of 100. So the probability of exactly 2 defective is 6 choose 2 times 1/100th to the second power times 99/100th to the 4th power. You could also write that as 6 choose 2 0.01 to the second power, 0.99 to the 4th power. That's probably easier to type in the calculator. So if we do that, 6 choose 2 times 0.01 raised to the second power times 0.99 raised to the 4th power. So there's a very small chance that we're going to have exactly 2 defective light bulbs. It turned out to be 0.00144. So less than 1%. So it's 0.144%. So that's a very small likelihood that if we buy a 6-pack of light bulbs, that we're going to have 2 of them being defective. Okay, so that's a good thing that that's a really small percentage. Okay, now what is the probability that no more than 2 are defective? So we hope for a high percentage here because I wouldn't think that you would buy very many packages that have more than 2 defective. So probability of no more than 2. So no more than 2 means it could be 2 or less. So probability of no more than 2 would be the same as the probability of none plus the probability of exactly 1 defective plus the probability of exactly 2 defective. Okay, so the probability of none defective, that means all 6 of them are good, and so that's 0.99 to the 6th power. We don't have any that are defective. Then the probability of exactly 1 defective, so that's 6 choose 1, which is just 6 times 0.01 to the 1st power, because that's the defective one, and that means we'd also have 5 that are not defective, so 0.99 to the 5th power. And then probability of exactly 2 defective, That is the one we already calculated from part A. That was 6, choose 2, 0.01 to the second power, and 0.99 to the fourth power. And so if we put all that on one line on the calculator, I'll show you what that would look like to type that in. So we have 0.99 raised to the sixth plus 6 choose 1. So parentheses 6 choose 1. And by the way, that is just 6. So if you already know that 6 choose 1 is 6, you don't have to put in the choose. You could just put in 6 times 0.01 raised to the first power times 0.99 raised to the fifth power, and then plus 6 choose 2 times 0.01 raised to the second power times 0.99 raised to the fourth power. And that turned out to be 0.99998. Four nines and an 8. So that's a very small outcome. So 99.998% of the time, 99.998% of the time, we're going to have no more than 2 light bulbs defective. So that's a good thing. And then part C, what is the probability that at least one of them is defective? So think about this, at least one defective. So that could mean there's 1 defective, or that could mean there's 2 defective, or 3 defective, or 4 defective, or so on. So probability of at least 1 defective would be the probability of 1 defective plus the probability of 2 defective plus the probability of 3 defective, and so on until we get to the last one, which is the probability that all 6 are defective. Okay, so that would be a lot of individual probabilities that I would need to calculate, and it would come out correctly, but there is a quicker way. When you're doing at least 1, I think we touched on this earlier on in the course, the probability of at least 1 defective is the same as the probability of, so it'd be the opposite of none being defective. So it would be 1 minus the probability of none. So that's the complement. Remember, we talked about the complement before. The complement of at least 1 is none. So 1 minus the probability that none are defective. So that would be 1 minus none defective would be when we have all of them being good. And so 0.99 to the 6th power. So that is 1 minus 0.99 to the 6th. Turned out to be 0.0585. So that is about 5.85%. So about 5.85% of the time, you're going to have at least 1 defective. So 5% is not very often, so that's pretty good. But occasionally, there is going to be a package that has a defective one about 5% of the time, about 6% of the time. Okay, so now that we've gotten a little bit of work with finding probabilities involving binomial distributions, we can also calculate the mean, variance, and standard deviation of a binomial distribution. And so here, let's take a look at A basketball player makes 88% of his free throws. Assume he shoots 10 free throws in each game. Find the mean, variance, and standard deviation for the number of free throws he makes per game. So the mean, mu, would be the number of free throws. So he shoots 10 per game. And the probability that he makes them is 0.88. And so that would be 8.8 successful shots per game. So we're saying that's his average. If he plays several games, if his shooting average is 88%, he's going to make about 8.8 shots per game. Okay, that would be his average mean. The mean is the same as an average. Okay, and then the variance. The variance, it says, is the number of trials, 10, times the percent of success. So the P again is the probability of success, and Q is the probability of failure. Okay, so 0.88 times Q, the probability, if he's got an 88% chance of making the shot, then he has a 12% chance of missing the shot. So it's 10 times 0.88 times 0.12, and that is 1.056, so that's the variance. And then the standard deviation is just the square root of that. And that is 1.0276. And so it's saying the standard deviation is about 1. So think about where your middle is. So if our average is 8.8 and we go 1 unit in each direction, that puts us at 9.8 and 7.8. So we have a lot of games that are kind of in this range. Remember, we said that 65% of the, in a normal distribution, 65% of the numbers will be within 1 standard deviation. So we're saying our standard deviation is about 1 unit. So about 1 unit takes me to 0.98 and 7.8. So about 66% of our games, he would be somewhere between 7.8 free throws and 9.8 free throws. Okay, this doesn't exactly fit a normal distribution because there's a limit to how high it can go. Obviously, he can't make more than 10 of them, but in a normal distribution, it would show it going on beyond 10. You get the bell curve here. But I just wanted to kind of relate that to the bell curve so you'd understand what this 1.02 means. That's the standard deviation, and so we expect most of the data to be within 1 standard deviation. Okay, and then our last one, if we roll a normal 6-sided die 100 times, find the mean variance and standard deviation for the number of threes that will be rolled. So we're seeing how many threes are going to be rolled. So the P would be the probability of rolling a 3, which is 1 out of 6 because it's a 6-sided die. There's only 1 3 on that 6-sided die, so that would be 1/6, which means Q would be the probability of not rolling a 3, which would be 5 out of 6. And so our mean would be 100. That's the number of trials, and n equals 100 times the probability, which is 1/6, or P. And so that is 100 times 1/6 is about 16.667. So on average, if we roll a die 100 times, on average, we're going to get about 16 to 17 threes. Okay, most of the time, or on average. And our variance is 10 times 1/6 probability of success times the probability of failure, 5/6, and that turns out to be 13.889 or 125 over 9. And then our standard deviation is the square root of that. And that turns out to be 3.727. So again, imagine you're at the mean, okay? One standard deviation to the right would be around 20, and one standard deviation to the left would be around 13. And so you're going to get a lot of, if you did this many times, if you did this experiment many times, you'd have a lot of games where it was between 13 and 20 threes that you would roll. Okay, so that completes the notes for 5.3 and also completes the notes for the whole chapter. So on your Chapter 5 student notes, I think we've done everything up through lab problem 5, so you can start where it says binomial distribution, and you should be able to do the whole rest of the packet now. There's a mixture of problems here. These are not all binomial problems, so you maybe have done some of them already. But anyway, go to the end of the packet, do all the problems that you have not yet done. And that's it. Have a good night.